The sky was not a mere canvas of distant stars but a dynamic, evolving theater of powerful forces that shape the formation of galaxies, stars, and even the fundamental elements comprising life on Earth. The iron in our blood, the calcium in our bones, and every element heavier than hydrogen owe their existence to nuclear processes within stars. Through the intense heat and pressure of stellar cores, atoms fuse to form heavier elements, which were later released during violent stellar explosions known as supernovae. This process, often referred to as cosmic alchemy, demonstrates the intimate connection between the birth, life, and death of stars and our very own existence. Matter, including the human body, is composed of star-forged elements, linking us to a greater universal narrative where the cycle of stellar death births the building blocks of life. In recent decades, fueled by incredible advancements in technology, scientists have been able to peer deeper into the structure of space and time, turning their focus to one of the most mysterious and iconic stars visible from Earth, Betelgeuse. Nestled in the shoulder of the Orion constellation, Betelgeuse has long captivated astronomers and stargazers alike with its brightness and distinctive reddish hue. But it is not merely the star's prominence in the night sky that has drawn renewed attention, it is its recent unpredictable and dramatic behavior. Once among the brightest stars seen from Earth, Betelgeuse has begun exhibiting a strange pattern of variability in its luminosity, a behavior that includes violent pulsations and unexplained dimming events. These fluctuations have led some scientists to speculate that Betelgeuse may be entering the final stages of its life, a phase that could culminate in a spectacular supernova explosion. This erratic behavior has prompted global scientific scrutiny, with observatories around the world training their instruments on this distant yet strangely intimate stellar neighbor. Despite appearing as a relatively dim reddish speck to the naked eye, Betelgeuse is anything but ordinary. With an estimated mass around 20 times that of our Sun, it stands as one of the largest and most luminous stars ever observed. Its true scale is staggering. If placed at the center of our solar system, Betelgeuse's outer layers would engulf the orbits of Mercury, Venus, Earth, Mars, and even extend past that of Jupiter. It lies approximately 640 light-years away from Earth, a relatively short distance in the vast expanse of the cosmos. Even traveling at the speed of light, which far surpasses current human capabilities, it would take over 6 centuries to reach it. Using our current propulsion technology, such a journey would take millions of years. This great distance does not lessen the importance of Betelgeuse's recent changes. Rather, it magnifies them, offering an unparalleled opportunity to observe the aging process of a massive star in real time. Betelgeuse is known to be a pulsating variable star, meaning it experiences natural cycles of expansion and contraction that affect its brightness. As the star expands, it emits more light and appears brighter from Earth. Conversely, when it contracts, its light output dims. Scientists have tracked 2 primary brightness cycles in Betelgeuse, one lasting approximately 185 days and another that spans about 2,300 days. Yet recent events have deviated from these known cycles in both magnitude and unpredictability. In early 2020, Betelgeuse underwent what became known as the Great Dimming, during which its V-band magnitude dropped to around plus 1.61, a significant reduction in brightness that sparked widespread speculation about an impending supernova. Although this theory remains unconfirmed, the event highlighted the star's instability and intensified efforts to monitor it closely. Part of Betelgeuse's signature red coloration is due to its relatively cool surface temperature, about 3,500 Kelvin, substantially cooler than our Sun, which has a surface temperature of roughly 5,500 Kelvin. This lower temperature means Betelgeuse emits less energy per unit area despite its immense size. Its recent dimming events are thought to be connected to changes within the star's internal structure, especially within the outer helium shell where fusion continues. As Betelgeuse ages, it moves from fusing hydrogen to fusing helium and eventually to heavier elements such as carbon and oxygen. These transitions cause bursts of energy that ripple outward through the star's layers, leading to expansion, contraction, and mass loss in the form of strong stellar winds. These processes create a type of stellar heartbeat, rhythmic fluctuations in brightness that can be observed from Earth. Astronomers use advanced observational techniques to study these phenomena. Photometry tracks changes in the star's brightness over time, while spectroscopy breaks down the star's light across different wavelengths to identify chemical composition, surface temperature, and radial velocity, the speed at which parts of the star move toward or away from Earth. In tandem with these observations, researchers rely heavily on sophisticated computational models that simulate Betelgeuse's internal processes. These models incorporate physics equations governing stellar structure, convection, and thermonuclear reaction rates to predict future behavior and explain recent changes. One significant factor in Betelgeuse's irregular luminosity is convection, the rising of hot plasma from the star's interior and the sinking of cooler material. Betelgeuse's convective cells are thought to be enormous, possibly larger than Earth itself, and changes in these cells' efficiency and organization can cause dramatic and seemingly erratic shifts in brightness. Additionally, expelled gas and dust from the star can form clouds that obscure its light, leading to temporary dimming not directly related to intrinsic luminosity changes. Though generally considered a solitary star, scientists have explored the possibility that Betelgeuse may have a binary companion. In binary star systems, two stars orbit each other, sometimes exchanging mass in ways that alter their evolutionary paths. Such an interaction could lead to enhanced pulsations, altered brightness, or even accelerated fusion processes. While no conclusive evidence of a companion has been discovered, the idea remains a tantalizing possibility, adding complexity to models of massive star evolution. The most dramatic and widely anticipated scenario, however, is that Betelgeuse is approaching the end of its life and may soon go supernova. Like all massive stars, Betelgeuse maintains a delicate balance between the outward pressure of fusion and the inward pull of gravity. When its core begins to produce iron, fusion grinds to a halt. Iron does not produce energy when fused, unlike lighter elements. Without outward pressure to counter gravity, the core collapses rapidly, triggering a massive explosion that ejects the outer layers into space. If Betelgeuse were to explode as a supernova, the event would be visible even during the day and could outshine the full moon for weeks or months. Its brilliance would become the most prominent object in the night sky, marking a once-in-a-civilization cosmic event. Fortunately, Betelgeuse is distant enough from Earth to prevent any catastrophic consequences. But if such a supernova occurred closer to our planet, it could produce gamma-ray bursts capable of stripping away Earth's ozone layer, increasing harmful ultraviolet radiation, disrupting ecosystems, harming human health, and damaging global agriculture. The electromagnetic pulse from such an explosion could also interfere with satellites and electronic systems on Earth. Luckily, Betelgeuse poses no such immediate threat due to its distance. After the explosion, the remaining stellar core could collapse into a neutron star or, if massive enough, a black hole. A black hole formed from Betelgeuse would be a fascinating object to study, as it would emit intense radiation from an accretion disk as matter spiraled inward, allowing scientists to explore extreme gravitational and quantum environments. Regardless of the final outcome, the fate of Betelgeuse will mark a major milestone in our understanding of stellar evolution and the life cycles of massive stars. Whether it ends with a dazzling supernova or a quieter transformation, Betelgeuse's changes serve as a profound reminder of the forces that govern the universe. These subtle yet monumental shifts in Betelgeuse's behavior have galvanized an unprecedented global effort to monitor the star more closely than ever before. Advanced observatories like the European Southern Observatory's Very Large Telescope and NASA's Hubble and James Webb Space Telescopes have joined forces to dissect every nuance of its changing state. Astronomers are capturing high-resolution imagery, studying the detailed spectra of the star's emitted light, and analyzing changes in infrared and ultraviolet emissions to develop a deeper, multidimensional picture of what may be occurring within the dying star's layers. The Great Dimming event of late 2019 and early 2020 was particularly shocking, so dramatic that it was visible to the naked eye by seasoned skywatchers around the world. Some initially theorized that Betelgeuse was about to go supernova, as no previous dimming had ever been as intense or rapid. However, as more data poured in, another plausible explanation emerged. The dimming may have been caused by a massive ejection of material that formed an opaque dust cloud, temporarily obscuring the star's light from Earth. This event highlighted just how dynamic and unpredictable massive stars can be during their twilight years and underscored the importance of long-term observation in understanding stellar life cycles. In addition to observational efforts, theoretical models have been refined to match real-time data more accurately. By using supercomputers to simulate the internal dynamics of Betelgeuse, scientists have begun to map out scenarios that could account for the irregular light curves and surface temperature changes. Some models suggest that we are witnessing Betelgeuse in a late helium burning phase, during which the star experiences dramatic interior rearrangements. These internal changes ripple outward, triggering surface turbulence, mass loss, and altered luminosity. Other theories propose that the red supergiant may be undergoing a series of complex, overlapping pulsation cycles, which can amplify or dampen each other in unpredictable ways. This possibility makes it even more difficult to determine when or if Betelgeuse will ultimately explode, as the signals leading up to such an event may be masked or mimicked by other natural oscillatory behavior. The notion of Betelgeuse having a binary companion, while still unconfirmed, continues to be a tantalizing possibility. If it were true, such a relationship could account for some of the star's oddities. Binary companions can siphon off mass, destabilize stellar envelopes, or contribute gravitational energy that affects the star's expansion and contraction phases. Astronomers have examined high-resolution images and spectral data for signs of a faint companion star orbiting Betelgeuse, yet none has been conclusively detected. If a companion does exist, it might be obscured by Betelgeuse's immense brightness or by intervening stellar winds and dust. Even the suggestion of a binary system adds layers of complexity to models of the star's end-of-life evolution and raises intriguing questions about how common such interactions might be among supergiants in our galaxy. The eventual death of Betelgeuse, whether it occurs in the near future or centuries from now, is destined to be one of the most scientifically valuable stellar events of our time. When a star of this magnitude ends its life in a supernova, the explosion serves not only as a cosmic light show but also as a forge for the universe's heavy elements. Ironically, the creation of iron in a star's core marks its demise, since iron fusion consumes energy rather than produces it. Once enough iron accumulates, the core can no longer sustain the gravitational pressures pushing inward, and a collapse begins. In mere seconds, the entire core of the star implodes, triggering a rebounding shockwave that tears the star apart. Neutrinos, a flood of nearly massless particles, escape in a dramatic burst, offering the first signal of the impending explosion. If Betelgeuse were to go supernova today, neutrino detectors on Earth would likely pick up this surge even before light